To locate the surface map, we are going to go to our first tab, the Information and Resources for NASC 102 Summer 2020. And if you scroll down to the area that is titled Maps to Use for Your Forecasting, then look for Surface Map. And if we click on Surface Map, lo and behold, there it is.
I will see what we call a current surface map. And there are a lot of things on here, and you've probably recognized some of these if you spend any time watching the weather, your local weather forecast, or the Weather Channel. But you see a map of the U.S. here, and you see a rather colorful map. You'll notice there are these L's, and these L's stand for low pressure. In Chapter 1, as you're reviewing the video in Chapter 1, you will see what the definition of pressure is. It's the amount of force per unit area we define as pressure. So if you take a column of air from the top of your head all the way up to through the atmosphere, you have molecules. You have molecules of nitrogen, oxygen, water vapor, and they all will exert a force over your head, a unit area. So that's how we measure pressure. The H's on here stand for high pressure. These are areas of higher surface pressure. You'll also see these lines. Notice this line of, we talked a little bit about this in a previous video. This is what we call a warm front. And notice the semicircles around the warm front. That indicates the direction. So this particular warm front is moving to the northwest. And then you see alternating lines of blue, red, blue, red. This means, or this indicates, a stationary front. In other words, the front is not moving. You'll also notice these dashed lines, and you'll see these quite a bit during the summertime. These are what we call low pressure troughs, or just basically areas of lower pressure. They're not fronts because we don't see a temperature difference or even a humidity difference across this particular type of dashed line. If you want to, you can call it a wannabe front, a front that never quite made it. This out here in West Texas, although looks very much like a trough, is what we call a dry line. There's not really a huge temperature difference across this dry line, but there is a difference in the amount of relative humidity, in the amount of moisture. You've got drier air back behind this dry line and more moist air ahead of this dry line. Again, we'll talk about moisture in Chapter 4. I'm using some terminology here that you are not quite familiar with yet, but I want you to understand the features on a surface map. Now, if we look back here into northwestern Colorado, you will see a cold front that I'm outlining here with the cursor. Notice the triangles, and it's indicating the motion. So this front is moving to the southeast. But we don't know how fast it's moving. We'll figure that out very soon in a lab that you have coming up. So again, we have a stationary front here, a cold front here, and then a pretty well-defined warm front over portions of the Upper Peninsula of Michigan, Minnesota, cutting through southeastern North Dakota and into South Dakota. So the warm front is moving to the north. You'll see another trough of lower pressure. Now the areas of green and even a little bit of pink that you see, looks like up over Wyoming, are indications of precipitation. And in fact, if you look up here at the top of the picture, the light green stands for light rain drizzle. Darker green, which you see in several of these areas, are indications of heavier rain. And we even see a little bit of rain, ice, snow mix here up in the higher elevations of Wyoming. Now, if you look at this particular map, most of the precipitation is located near a front or near a trough of lower pressure. If you look at high pressure, looking at these three areas of high pressure, you don't see any precipitation within several hundred miles. But we go to the stationary front down in the Atlantic, and you see some precipitation associated with it. So, as you'll learn later, the reasons behind this, typically, if you're going to have precipitation or cloud cover, it's going to be associated with lower pressure and fronts. Or you can have this low pressure here, and you get a little bit of rain around it as well. Around high pressure, typically you will see fair skies, light winds, beautiful days. Around low pressures, you will see clouds, rain, assuming you have sufficient moisture. And again, we'll talk about that in Chapter 4. Now, you'll notice these white lines here that I'm outlining. These are what we call isobars. Iso meaning same. Bar is a measure of pressure. It's a unit of pressure. We'll measure units of pressure in millibars. And when we're talking about air pressure, we're talking about air pressure that can range anywhere from 950 millibars to 1,050 millibars. The number 950 is lower than 1,050. So as the pressure begins to decrease, the numbers begin to decrease. That's an indication of lower pressure. The lowest pressure will be associated right around low pressure centers. As we begin to move away from the low pressure centers, the pressure begins to increase. And in fact, there's a local maximum called a high pressure system. But if I begin to move away from the high and move toward the lower pressure, eventually we reach a local minimum of lower pressure. Again, these white lines are what we call isobars, and they're lines of equal pressure. Now, what's really nice about these isobars is that we can count the number of isobars across Iowa and infer wind speed and even wind direction. Around low pressure, winds blow counterclockwise, just how I'm using the cursor. So out ahead of low pressure, you would have south-southwest winds. Around high pressure, the winds blow clockwise. So if the winds are blowing clockwise around high pressure and counterclockwise around low pressure, winds on this map would indicate a south-southwest wind across the state of Iowa. So just by looking at a surface map, you can infer several things. You can identify if precipitation is going to move in. You'll see the locations of fronts. You can figure out wind speed, wind direction. There's a lot of things that you can find out from a surface map. Now, one trick you can use is that you can count the number of isobars across the state of Iowa, and each isobar would represent 5 knots. Now, it depends. Actually, we've got to look at something here. If the Weather Channel is using 4 millibars for each of these isobars, in other words, pressure is dropping by 4 millibars every time we encounter one of these isobars, then we can say that this is akin to 5 knots, 10 knots, 15 knots across Iowa. If they're using 2 millibars intervals, 2 millibar intervals, in other words, pressure is decreasing by 2 millibars, then we would divide that 15 in half and roughly call it an 8-knot wind. Now here's how I can figure this out. If I go back to surface, and you've seen this in the temperature video, I've shown you this particular where you go to the University of Illinois, And we look at a station model. And in fact, let's just go to the Northern Plains station model. And you see wind directions. By the way, the station model is one of the first assignments, so you should be able to understand how to read these now. But across Iowa, it looks like we've got 15 knot winds in southern Iowa, 15 knots in Des Moines, 20 up in northeast Iowa, 25. So we've got winds 15 to 25 knots out of the south. South, I would say these are basically southerly winds. So what the Weather Channel is using, each one of these isobars, lines of equal pressure, represents 5 knot winds. So if I look at this 5, 10, 15, just by looking at this map, I can infer 15 knot winds. And in fact, that's what we saw with the station model across Iowa. So if fronts move some form of west to east, southwest to northeast, northwest to southeast, then these lines of equal pressure are going to move closer and closer to Iowa, which should begin to pick up our winds. So there's a lot of information you can glean from the surface map. So at this point, I will go ahead and end this particular video, and I will pick up with the 500 millibar surface.